So hello everybody, I'm Daniele Fontanelli and I work in the University of Trento, where I am an associate professor for the instrumentation and measurement topics. And in this tutorial I will talk about the measurement applications for autonomous systems. So whenever you talk about autonomous systems, there are different definitions depending on the research realm you are referring to. So for example, the three main definitions are autonomous system in the telecommunication field, in which they are referring to systems that works on the network having a set of IP addresses that has the same kind of features, or there are other definitions that come from mathematics, in which autonomous systems are systems that depends only on the variable x and does not depend on any other endogenous variable. In this slide, in this tutorial, I will present a particular class of autonomous systems that are basically mechanical platforms that are autonomous and there's some level of autonomy, and which are called robots. So what does it mean to be an autonomous system in the robotic fields? It means that the robot has some characteristics that allows them to do some work in autonomy. So for example, self-maintenance, or sense the surrounding ambient around the robot, or performing a task, like for example, you may think about robots that cleaning rooms in private houses, or also navigation, which means to move from 2 points inside an environment that can be indoor or outdoor. So robots are very important nowadays, so you may think about the Industrial Revolution, in which the robots actually play a very important role in the development of new industrial ways to produce goods. And a very nice definition about robotics is given by Professor Bruno Siciliano, that defines the robotics as the science studying the intelligent connection between perception and action. And for people working in measurements, the most important feature is perception. So the things that allows the robot to understand the environment and also its own status, its own posture. So whenever you deal with robotics automation, you start basically from the plant, that is basically a robot, and from the robot you derive a model, a mathematical model that can be treated in an analytic way. So given the model, then you connect the model to a set of sensors that are able to capture some information about the environment, about the robot per se. Then the output of these sensor systems goes through a control loop that uses this information to compute a set of signals that then are fed to actuators, that are the elements that allows the robot to interact physically with the environment. So if you put it into a description that is more high level, basically we have a plant, we have the controller, we have the actuators, but also we have this important component that is the measurements, basically, that comprises sensors and estimation algorithms that are able to derive meaningful information from the sensing data. So basically, autonomy is a collection of, it's based on three main pillars that are perception, control, and actuation. So basically the senses that allows the robot to understand the environment, the brain that compute the control actions, and the actuations that are basically the muscles of the system. So whenever you have to do with autonomy and with robotics, you have to basically face with three main questions that are more relevant for mobile robots, so for robots that move inside the environment. So the first one is, where am I? Which means that we have to understand where the robot is inside the environment in order to carry out its task. And the solution is the localization problem, or position tracking of the robot inside the environment. The second question is, where am I going? And in order to answer this question, usually you have to plan a path inside an environment, which means that you have to determine what is the best route that leads the robot from one point to another one. And finally is, how do I get there, which is a set of control laws that allows the robot to actually perform the planned path. So let's start with the first problem, that is localization, that is maybe more interesting from a measurement viewpoint. So with localization, we start with a basis of knowledge that in practice are a map of the environment, which is given in terms of metrical descriptions or topological descriptions, depending on the features that are the components of the map that we are modeling in some sense. For example, a map can be given by a set of walls that defines the environment inside which the robot is actually moving. Then you have a set of measurements that in this case are collected from a laser that senses the walls inside the environment with a series of points. And from these points you can extract features that are components that describes the set of sensors, of sensor readings. Then you have to put these two information together, which are basically prior information about the environment and new observation of the environment, new measurement, and then you try to match these two information together and then to fuse them coherently. And so to fuse the prior knowledge with the likelihood of the measurement given the prior knowledge. And this is can be done using, for example, Kalman filter or Markovian filters that tries to fuse together prior information that basically comes from odometry of the robot with the newer observations coming from the sensor. So the localization problem is an issue that allows us to estimate the robot's position inside an environment using a priori knowledge that are basically the maps. In order to carry out this problem, we need to use a set of sensors. Usually sensors are divided in two classes. One refers to sensors that are able to understand the motion of the robot, basically the ego motion of the robot. So proprioceptive sensors like encoders, accelerometer, or gyroscope. And then there are also another set of sensors that instead was main objective is to extract information from the surrounding environment. Whenever these information are not useful or not sufficient in order to reach a predetermined target uncertainty, then you need to add additional markers that are basically features that are already mapped inside the environment in order to keep the localization uncertainty below the desired threshold. So basically, to estimate a position of a robot in a mapped environment, you need, of course, a map and a reference frame. You need to understand the initial condition of the robot, and then you have to keep tracking the position of the robot inside the map. If you're not interested in tracking continuously the position of the robot in the map, then there is a sub-problem of this one that is called positioning, in which you are simply interested in determining what is the actual position of the robot, and so the fixed position. In this case, the position of the robot is no more a variable that changes in time, but it has just a fixed variable, and so it can be fixed as, it can be considered as a constant parameter with a known value. So let's speak about positioning. So imagine that you have a robot that is moving in a corridor, and so this problem can be modeled by considering the robot with having a certain position along an axis. So in ideal condition, it is sufficient to have just a sensor that senses the position, and so we are able to, given the measurement Z, to reconstruct the position X of the robot inside the corridor. Unfortunately, whenever you have noisy data, of course, one measurement is no more sufficient, so you are collecting more measurement, and so this is the possible model in which the position of the robot is affected by random variables representing the noise that usually is considered as zero mean and with a certain variance. Whenever you are in this setup, there is a very simple solutions that can be used in order to infer the value of X that I will remind that is just a fixed parameter with a known value, because we are talking about positioning. And so you can use the weighted least squares solution. So in the weighted least squares, whenever you have a linear relation between the measurement and the quantity to be estimated, you can simply solve an optimal problem, an unconstrained optimal problem, and so the best estimate is given by the solution of this minimization problem like this, in which we have a weighting matrix between the measurement and the quantity to be estimated. The solution is quite simple, and it is the pseudo-inverse, and it is a weighted pseudo-inverse because, once again, we have a weighting matrix W that I will talk about it a little bit in more details in a few slides. So the main problem about this approach is that whenever you are collecting a lot of measurements, this computation here of the pseudo-inverse becomes very difficult and also computational demanding. And so the best way to deal with this problem is to take the set of measurement here and then divide it by chunks with a set of uncorrelated measurements, and then use this set of measurements once at a time, which means that we can use the first one to implement just the standard weighted least squares, and in this way, so just using just z of 0, that is the first set of measurements, and then we can also estimate the uncertainty that is related to the estimation error of x hat of 0 with respect to x. And then we can go into a set of iterative steps in which we are using the different chunks of measurements one after the other one. And each time we are also estimating the error covariance and propagating the error covariance. So this is basically how the algorithm works. We have an initialization step that uses just the first set of measurements, and then we go through into a set of iterations using new information coming from the sensor. A few remarks of this approach is that the weighting matrix is just the inverse of the covariance matrix of the measurements. The innovation, that is the difference between the actual measurements and the estimated measurements, is given, of course, by a mathematical difference between z and the forward map of the unknown x. And associated to the innovation, there is also the covariance matrix, so that measures the uncertainty in this innovation. That is the matrix S that is used to compute the gain, and with the gain we can update the estimate and also the covariance of the estimation error. A nice interesting thing about this solution is that for Gaussian noises, the weighted least squares is exactly equal to the maximum likelihood approach. And it's also a best linear unbiased estimator if the noise is not Gaussian, but the relation between the variable x and the measurement is linear. This is, of course, a non-Bayesian filter because we are treating x as a constant. Whenever instead we have some information about the motion of the point, in this case, or the motion of the robot, we can identify the position of the robot as pk, where pk plus 1 is just the next position of the robot, and we assume to know the model. So in this case, we can first consider the motion of the point on the line and use it as a prior, which is, of course, based only on the knowledge about the model. And then using the likelihood, that is basically the statistical description of the innovations. So with respect to the weighted least squares, if you apply the prior, basically what changes is the first part, because the second, that is related to the likelihood, is exactly equal to the weighted least squares, so nothing changes here. The main point here is that instead we can make use of the prediction, which is our additional knowledge about the model. So in some sense, in this frame here, we are feeding into the estimator the additional information that comes from the knowledge of the model, and this is the quite known Kalman filter. The Kalman filter is, of course, a Bayesian filter because it puts together prior likelihood, and basically it computes the statistical description of the estimates using the posterior, that is the conditional PDF, and uses information the prior, that are the statistical description of the model knowledge, and the likelihood PDF. Kalman filter has a lot of positive features. It is optimum with respect to the variance when the noises are Gaussian. It is the best linear estimator when the errors are not Gaussian. Of course, there are several different variations of the Kalman filter, depending on the fact that we are using a model that is discrete or continuous, and the measurement model that is discrete or continuous. And also, there are solutions for nonlinear systems, for example, the extended Kalman filter or the unshanted Kalman filter, and there are also solutions whenever the dynamic of the system that we are considering. So the model is not defined, but can change depending on time, which are called interactive multiple models. So let's switch back to the problem of localization. So basically, applying a generic localization algorithm is not always working. So for example, let's take a look to one of the possibilities that you may use, that is to use a dead reckoning approach, in which the position of the system is reconstructed by successive set of relative measurements. So in this case, this is more or less the same, or just using the information about the model, because we are not collecting any other information than just the relative motion of the system. And so this may generate large uncertainty in the estimate that finally grows unbounded. This is instead, this is just an example that is the difference between the ground truth, that is the red line, and the blue line, that is the measured position whenever you use dead reckoning. So as time goes by, as the robot moves, you have that the estimates diverge from the actual position of the robot. And this is exactly equal to the treasure map problem. So these slides simply show you that in order to have a very efficient localization algorithm, you have to fuse information that comes from the environment. So not only using ego motion information about the robot. And also this fact allows us also to reframe a little bit how algorithms about localization actually works nowadays in the field of robotics. So this is a description about accuracy and precision of measurements. And what happens actually about robots is that controllers are almost entirely related to the accuracy of the estimate, but not at all related to the uncertainty level, so to the precision of the estimates that we can collect. So precision turns to be a very important feature of a localization algorithm, because depending on the actual task that a system or robot should solve, an autonomous system should solve, you may need different levels of uncertainty. So how can we meet a desired target uncertainty for localization? Where there is one main solution, that is to adding landmarks. And this happens whenever you don't have enough information that comes from the environment in order to meet the desired target uncertainty. So more or less, this is very standard solutions that you can quite often and almost always apply, depending on the environment, of course. And from a measurement viewpoint, adding markers inside the environment means to add calibration point in which the systematic uncertainty contribution can be nullified whenever you step into or measure one of these landmarks. And the systematic uncertainty contribution, of course, comes from the dead reckoning phenomenon. So this is not at all something that is not applied in general applications. So this is just a video that I've taken from YouTube, from the Tech Revolution. And this one is just a comparison between the automatic solutions that you may find in warehouse for Alibaba and Amazon. And this is the example of Amazon, in which you may see there are a lot of robots Kiba. And the most important thing for our purposes is the presence of these landmarks that have been put onto the floor in order to minimize the uncertainty of the localization for this robot, and also to set up a set of fixed points that should be reached in order to move goods inside the environment. And this is more or less exactly the same kind of solution that you may find also in Alibaba robots. So once again, this kind of robots moves inside the environment and uses landmarks that are placed here, here and there inside the environment, exactly with the same kind of purpose, that is to reduce at most the uncertainty about the localization. The problem of precision, it's also quite relevant whenever you use not just fixed landmarks, but you may also use some, let's say, service that comes from the environment. So in this work, we have studied the problem of localization for robots, in which which has been used ultra-wideband solution for robot localization. So in this particular case, the ultra-wideband is used both for communication and for ranging measurement about the robots inside the environment. And the main problem is that we do not want to, we want to be scalable, which means that we want an arbitrary number of systems that are working in the environment and moves inside the environment, but keeping the structure of the ultra-wideband fixed, which means that we have to limit at most the ultra-wideband update request that comes from the robot. And so the main idea is to rely on the Kalman filter, and so on the Bayesian approach, which means that we are going with prediction, so using only the prior, so the motion of the robot, and then whenever we detect that the uncertainty is reaching the maximum allowable level, then in this case we are asking to the system to provide additional information from the ranging system that becomes let's say, a shared resource. So this way we can guarantee the desired level of precision for our system using a shared system for the ranging of the robot. So in this animation, you may see here that this is the statistical description of the error. So whenever the probability of having a large error increases, then the system asks for additional measurement from the ultra-wideband solution, and so we can reset and restore the systematic errors. And this, of course, this is a simulation, but we have made an experimental validation, and in this case, we have a robot that moves, and on this red X here, those are the points in which the robot asks for ultra-wideband data in order to keep the uncertainty beyond a certain limit. So let's go very briefly to the third point, that is the control and navigation. Let's see how, again, uncertainty plays a role also in this kind of systems. So this was just the first picture in which we have the description of our system, and we have here the main component, that is sensors and estimation. So in robotics application, again, usually for control application, you usually make up for accuracy. That is, how accurate is your data with respect to the actual position of the robot. But in our idea, precision also plays a fundamental role. And we may see just by simply presenting a very simple task, a very simple navigation task for a robot. So in general, control problems for robotics can be divided into three main classes that are stabilizing on a point, following a path, or try to track a desired trajectory. Let's focus on path following. And let's see how precision comes into play whenever you try to control a mobile robot. So this is an example that comes directly from an application in which you have a robot that helps a person, a senior, to walk inside an environment. You may think about a trolley, or you may think about an automatic wheelchair. So the main problem is to let the person move along a desired path, that is this path. So this is actually what happens if the person tries to follow the path, which means that it follows this dashed line here, but the estimated position diverges from the actual position of the robot. This is because we have an estimation algorithm, and so we have uncertainty in tracking the position of the robot inside the environment. So if you revert this problem and you simply do not observe the robot that is moving when you try to control the robot, This is actually what happens. That is, the only thing that you can do is just to try to control the quantities that are known, that are the estimated position. So if you try to control the estimated position on this path, it happens that the actual position diverge, and if you are in a constrained environment, this may generate accidents, and the robot may hit the wall, for example, if you're moving into a corridor. So the basic idea of this kind of application is that the uncertainty that you have in your measurement plays a fundamental role. And whenever the uncertainty grows too much, then you have to leave the control to the human and do not keep controlling the robots, because you may end up in this kind of situation. So we have applied this very simple idea to a robotic trolley that is used for the motion of persons inside the environment. This is our robot that is basically a standard trolley that is equipped with some additional features. So we have a computer here, we have a set of sensors, we have actuators on the rear wheels. We have some sensing system for the localization. So we have encoders on the rear wheels of the robot, but we have also here a camera that is able to detect the markers that are placed on the floor in order to localize the system inside the environment. The basic idea comes from the fact that is, let's say, a control law is asymptotically stable whenever a certain function that is called the Lyapunov function has its time derivative that is negative. Of course, if you know exactly the quantity of interest, then it is easy to, if you know exactly what are the characteristic of your Lyapunov function, it is easy to simply define a control law that lets this Lyapunov function to be negative. The problem is that whenever you have uncertainty, you are not 100% that your Lyapunov function will be negative definite. So in this case, whenever the confidence about the probability of having this function negative decreases upon below a certain value, a certain threshold, then the thing that you have to do is to let the user control, or if you are enough confident, let the robot to control. So basically, when you have low uncertainty, you can let the user control. If you have high uncertainty, you can let the robot to control the system. And this is actually an experiment in which we try to implement this kind of sharing of authority in controlling the robot. So in this case, the robot is moving and detects this marker, and so it starts to control the vehicle, and then the uncertainty grows, and whenever it goes above a certain threshold, then it is the user that is in control of the robot. But if the user tries to do strange things like, for example, making a U-turn inside the corridor, what happens is that the robot starts to control the robot and starts to keep the control of the system and put the user along the correct path. If the user is moving in a correct direction, and if the uncertainty grows, you simply let the user to go along the corridor, avoiding to control it, because, for example, in this case, if you try to control the robot with this very high uncertainty, you end up in let the robot to go towards one of the walls. So again, to summarize, the autonomous mechanical systems that are being considered in this tutorial are basically robots. And for these robots, sensors and measurements are fundamental and play a fundamental role. We have seen that there are three major problems for robotics that are basically localization, planning, and control. And in all of these the three main pillars that guarantee the robot to be autonomous, precision and uncertainty plays a fundamental role.